Welcome back to the third part of this lecture on rolling element bearings. And in this part I will be talking about failure of rolling element bearings and wear mechanisms in rolling element bearings. Now the important thing is to remember that most bearings actually will outlive the machines. I've shown some figure here of around 90% of the bearings that actually outlives the machine that the bearing is mounted in. A little bit less than 10% are replaced for security reasons. I mean, you do regular maintenance and you replace bearings that you expect are about to fail. And bearing failure, that accounts for the remaining 0.5% of the bearings. That may seem very insignificant, but it is a very important part to investigate and to work with, because a production line standstill in a huge process industry that can cost you some tens of thousands of euros per hour, or even hundreds of thousands of euros per hour. And if that is due to failure of bearings, then you really need to put effort into understanding why and how to prevent that. So typical mechanisms that you encounter is fatigue, of course. You have fracture of the bearing, plastic deformation, electrical corrosion, electrical erosion, corrosion of the bearing, abrasive wear, and adhesive wear. And I'll be discussing these individual mechanisms a little bit more in detail. Starting with rolling contact fatigue. The bearing life is typically limited by the RCF, or rolling contact fatigue, which is induced by the cyclic or repeated loading on a very small surface. Typical damage would look something like you see here in this raceway of an actual ball bearing. And what happens is that maximum shear stress, as we were discussing earlier in part 2, occurs at some depth below the surface. So if you look at this figure, you have the maximum shear stress as a function of depth here, and your maxima will occur at some point below the surface. And if this stress maxima would coincide with some defect in the material, like impurity, dislocations, or something else, you may end up with a crack initiation in that specific point. And this crack will then grow. You will have a crack propagation in the material, and it grows up to the surface and results in a piece of the material being removed, leaving a pit formation, as you see up here. That's why this mechanism is also known as pitting sometimes. You may also have what is known as surface initiated damage. And this occurs when you have asperity contact, like this and this and this, due to, for instance, poor lubrication, and you get metal-to-metal contact. During this interaction between the asperities, you may also have some micro-crack formation, which results in small fragments of the material being removed, leaving micro-pits on the surface. So you can actually see here in the image to the right what a typical surface initiated damage pattern would look like. Regarding the subsurface initiated damage, as I said, this occurs due to the stress maximum at some depth into the material, and it can result in crack initiation and propagation. So you can see that here, where you have a crack initiation, and you can also see that here in this figure right here. And here you can also see how this how the microstructure of the material is also affected by the number of revolutions. You have 10 million, 60 million, and 600, more than 600 million here, where you actually start forming cracks at some point. And in the end, a typical appearance of pitting damage or subsurface initiated cracks, when it leaves a pit formation, you can see that in these images, typical appearance of that. Abrasive wear may also occur, which is when you have some hard particles typically entering into the system and removing material in that way. It typically results in a mirror-like finish on the raceway. Basically what you do is you introduce sort of a polishing action by the abrasive particles. And this can be caused by, for instance, particles and contaminants in the lubricant, and or combination of poor lubrication that you enter into more mixed lubrication regime, where you have more asperity to asperity contact, which may also give you a slight appearance like the one you see here. Adhesive wear can also be found in rolling element bearings, and adhesive wear is when you have for instance two metallic materials, steel on steel for instance, and you form strong bonds between the surfaces, and you basically take away material from, because the bond between the surfaces is stronger than one of the materials internal strength. And in a rolling element bearing, this would occur when the rolling elements are accelerated during re-entry into the loaded zone. Then the rolling element will suddenly accelerate. This will give you even more sliding during that acceleration, which result in heat generation. And heat generation is typically bad for the lubricating film, since the viscosity will drop of the lubricant and you will probably have a film collapse, the lubricating film, and therefore you have metal-metal contact and you form junctions between the surfaces, and you can transfer material between the race and the rolling element in this case. And this typically shows as a very rough surface, as a wear pattern, as you can see on the side here of the roller, for instance. Corrosion can occur in typically three different forms. You have moisture corrosion, caused by the presence of water, and when you do not have sufficient lubricating media present to prevent corrosion. You may also have what is known as fretting corrosion. If you have a very small movement between the ring and shaft or the housing, you can create, it's basically an adhesive wear process that initiates this, but the small amplitude of the motion will retain the wear particles in the contact, and these will oxidize and you will have the appearance of rust. What can be very negative for the bearing is that this affected area may act as fracture initiation sites, and you definitely want to prevent that. Then there's also something called false brinnelling, where you have a stationary bearing, and this bearing is subjected to vibrations, and this micro movement will cause a sort of fretting action between the rolling element and the raceway, to cause the micro movements will then cause some small initial adhesive wear. The particles will be retained in the contact, and basically what you will cause is small indents in the bearing, and these indents will then act as initiation sites for fatigue damage. Electrical erosion can also occur if you have an electric current passing through the bearing. The current will pass the small contact area or contact surface, which makes it very high energy density, and you will encounter very high temperatures. This will result in small craters that are formed where the material is melted. You can see the resemblance to arc welding. The damage will typically look like this in the microscope that you see here. You have even some material that has been thrown out from the actual crater. And these small pits or damages can of course also act as initiation sites for crack initiation and propagation. Overload typically is caused by incorrect mounting. You use excessive force or shock loading to the bearing, and obviously if the bearing is damaged, the races are damaged and so on, this will lead to vibrations, noise during startup and during operation, and your bearing will not function as intended, and you will probably encounter early failure also because you have stress concentrations in different parts of the bearing. Fracture can also occur for three different reasons. You have force fracture, for instance, caused by improper handling. There's also fatigue fracture that initiates when the fatigue strength is exceeded, and it leads typically to total fracture of the race or the ring. Thermal fracture may also be one reason for initiating fracture, caused by, for instance, frictional heating. The additive contents in the lubricant may also affect the bearing life. Now, you add additive to the lubricant to improve its, for instance, the load carrying capacity. Like this shows a so-called EP test where you increase the load continuously here, and at some point you get a weld point. You can see that for the EP oil this is much higher than for the base oil. But if you look at the number of revolutions and the life of the bearing, you get opposite behavior where the EP has a negative effect on the life of the bearing, and this is because of you have high chemical reactivity of the additives, and that has a negative influence on the life of the bearing. Now, when we talk about the life of the bearing, SKF, they have a theory for calculating the bearing life. This has been around for many years, accepted in 1947, called L10. And basically what you do is you compare the load rating of the bearing to the load that is applied to the bearing, and this right here is chosen whether it's a ball bearing or a roller bearing. Now, there is also a more extended formula where you have a reliability factor that accounts for the probability of a bearing to exceed a certain life, and the tribology factor, which you see right here, which accounts for cleanliness of the lubricant, the viscosity, fatigue strength, and so on. And the static load rating, if you use that here, that's based on the material hardness, whereas the dynamic load rating, which is also available, is based on the fatigue properties of the materials. So finally, if you look at the bearing system life, you need to consider a systems approach, because the whole bearing system, the life of that system will depend on the bearing life itself, the life of the sealing, the life of the grease, and also the life of the cage. And so you have to consider all these different components to assess the total bearing life or the bearing system life. That is also a very important point to remember. Finally, these are the references that you can look into more detail. Some of them are in English, some are in Swedish, but you may look into details and find further reading in these 3 references if you like. And by that, I thank you for your attention, for listening to this lecture, and I hope you have enjoyed it. Thank you very much.